Okay, I would like, first of all, to thank the organizers for the opportunity to give an update on Gravitational-Wave Space 2050. So as some of you may know, in June 2021, the Director of Science and the SPC of ESA announced the next program, science program, called the Voyage 2050, selecting 3 teams, confirming the recommendation of the senior committee. And I think people in this room are particularly interested in the 3rd team, called New Physical Probes of the Early Universe, trying to address questions like how did the universe begin, how did the first cosmic structures and black holes form and evolve. So the recommendation was to cover this theme with either a new gravitational wave mission or a cosmic microwave background experiment. So in particular, this new physical probe of the early universe will look at a high redshift, so let's say redshift larger than 8. And the idea is to, in the case of gravitational wave, to open a new spectral window either in the desi-hertz or microhertz, or perhaps also in the middle of the two. So for this exercise, several white papers were submitted to the archive and then published. You see them on the left here. And there was also a white paper for the decadal survey of astronomy and astrophysics in the US. And in the usual span of frequency and the characteristic strain of different sources that you can see here, so one possibility is to build a detector which goes more to lower frequency with respect to LISA, which is black here, which is called micro-RS, 10 times LISA, better sensitivity than LISA, Amigo, so still in the millihertz, or a detector in the desi-hertz. So in the spring-summer of 2022, the Gravitational-Wave 2050 working group was established by a steering committee following a suggestion of the executive committee of the LISA consortium. Quantitative work started in the fall of last year, and the goal is to produce a report that will synthesize the science cases for the different bandwidth, or maybe even selecting 1 or 2 of them, and the technological feasibility of a possible future gravitational wave mission beyond LISA. The working group is divided in a science group and an instrument design group. The science group has several subgroups, as you will see in a moment. People have been recruited worldwide, and at the moment we have around 60, 70 people that are actively contributing. So this is in full glory, the working group. You see on the bottom the different subgroups that cover different important themes with coordinators. And in fact, I thank the coordinators for providing several inputs for the preparation of this presentation. I will only highlight some of them because I have a very short talk today. So in fact, let me start with the instrument design group, which has as main task to think of a mission and develop a mission which will be in the cost envelope of an ESA-led mission, which is not easy, and also discuss the technological feasibility of that mission in the different bandwidth. So far, discussion that at the beginning involved also people from atom interferometry have converged on a mission that will use still laser interferometry, either a constellation on the Earth orbit of 3 satellites, as you can see here, more at lower frequency, or a kind of LISA mission, if it will be in the desi-hertz, will be much shorter, perhaps by a factor 25. So these people have, up till now, worked to provide a performance study to compare different mission concepts, which is made of different steps, as you can read here. And in particular, they have come out with the first version of a performance modeling tool that now the people working in astrophysics and cosmology can use in order to build the science cases. You see here some examples of the noise curve that you can produce with these tools. The big next step for this group is to investigate realistic technological development that can be available at the time of 2050. Now, to develop these science cases, as you can imagine, we need also to expand the LISA data analysis tools, and this has been done by the data analysis tools subgroup. So in these plots here, you see the TDI response for some of the sources, massive black hole binaries and stellar origin black hole binaries for emission in the microhertz, LISA max, and the decihertz. So let me discuss the first important science cases. So we are interested also, again, in black holes, because LISA will not discover all the black holes in the universe. And so one important class of black holes that in particular emission in the decihertz can target are the so-called intermediate mass black holes. These are also targeted by ground-based detector like Einstein Telescope Cosmic Explorer, but the ground-based detector will be able only to go up to a certain redshift, and even so will, in these cases, see only a very small portion of the waveform, perhaps the ring down or the merger ring down or maybe a cycle during the in-spiral. But with the decihertz mission, one can target up to very large redshift this class of black holes, which are very interesting because, again, are the black holes that, for example, are associated to the so-called light seeds, which are not going to be a target or mildly a target for LISA. And here are the ground-based detectors. So the stellar origin black hole, intermediate mass black hole binary subgroup is upgrading all the population catalogs for isolated dynamical channels at large redshift, because now we are looking at much larger redshift. And in particular, the codes called cosmic code and the BPOP code, producing the first results for the distribution in masses for these binary systems. You see here the distribution for the primary mass for isolated binaries and for primary mass for the dynamical binaries. And they are trying also to implement recipes for POP3 stars to model, in particular, the evolution of larger redshift. Now, this plot on the right is quite overwhelming. It's taken from the white paper in the microhertz, which at the time was called ARES, but the satellites were on the orbit of the Mars. But in the LISA max will be the orbit of the Earth, will be more realistic. And you see here the noise spectral density of a kind of detectors in the microhertz. And what I wanted to highlight here are these in-spiraling black holes, many of them that could be seen with the detector more in the low frequency, hundreds of years before merger. So this will be a more high redshift science case, but these detectors are going to see also the galactic center, black holes around Sagittarius A star, or even 100 of binary black holes in our galaxy. So the massive black hole binaries and extreme mass ratio in spiral subgroup is looking more in detail to these science cases, in particular for massive black holes at large redshift. They are trying to understand the astrophysical backgrounds, the unresolved ones on one side, because I want to emphasize that if you go to lower frequency, at some point you have to take care of the background due to the massive black hole binaries in our universe, which you see here. This is the galactic white dwarf background, and then at some point you have also the extragalactic white dwarf. They are also looking at a source that can be resolved, and in particular coming out with numbers of detection that you can have for massive black holes, for the decihertz, for the LISA max and also the decihertz, as you can see here. I wanted just to emphasize that for the mergers, there will be also, so for a system that are not just in spiraling, the localization of the skies is illustrated here in colors. And you can see also, again, with the decihertz going to very large redshift or moving more into a high mass binary, massive binary black holes. Now, another important theme of these new detectors will be actually the synergy with electromagnetic observations. For the decihertz, there will be an arc-mean angular resolution possible because of the long duration of this signal in the band. Something I will come back also in a moment will be the possibility with the decihertz to shed light on the progenitor of type 1a supernovae if they come from merger of white dwarf or from accretion onto a white dwarf of a main sequence star. With these black holes very far from merger, hundreds of years before merger, still with accretion disk that will be interesting synergies with UV and X-ray emission. And we will see many extreme ratio spirals, IMRI, in AGN, so not in vacuum. And also here, the combination with X-ray observation will be very interesting. So cosmography subgroup is looking in the possibility of measuring the Hubble constant or Hubble-Emet constant with much better accuracy because of this much better resolution I was mentioning before. There are also other ways actually of doing that. I wanted also to mention another interesting science case which uses the fact that using gravitational lensing you can have distortion in the waveform that can actually allow to observe dark matter halos. And in this plot here, you see the possibility with LISA max at the level of 64% to measure halos as small, in this mass range, which is actually not possible to observe with electromagnetic astronomy. So this is something still preliminary that people are looking on. Now, galactic compact binary subgroup, of course, is looking at low redshift. We are very much interested also in a high redshift. But if you have a mission that is targeting the high redshift, certainly you can have a much deeper characterization of the invisible stellar content of our galaxy. So this is very important. But I wanted to highlight here what I just said before. LISA, in 10 years, will have the probability of 4-7% to see a gravitational wave signal associated with a type 1a supernova event, if they are due to double white dwarf mergers. But with the DCRs, with an horizon distance of the Virgo cluster, we could bring this probability up to 100%. This will be really wonderful to see the gravitational wave signal then shutting off when there is the merger of the two white dwarfs. And this is a low redshift science on one side, but because of the implication, we will be able to understand the systematics of type 1a supernova, which are important for assessing the Lemaitre parameter, the Lemaitre Hubble parameter. This is also going to affect the high redshift science. So the multi-messenger astrophysics subgroup is looking also at all this connection with electromagnetic astronomy, in particular in this beautiful representation, the possibility of looking at the accretion disks around the black holes, the massive black holes, when they are still far away from merger. Now, the astrophysical stochastic background subgroup is looking at improving the predictions for the galactic and extragalactic astrophysical gravitational wave backgrounds. And I wanted to highlight something here, which is very important. If you want to go to a mission which is 10 times better than LISA, like AMIGO, or in the DCRs, you really have to target a high redshift. You want to make sure that we are not dominated by the astrophysical foregrounds. So in this plot, there is an update of recent results by Hayes-Nellemans group, where you see the extragalactic white dwarf binary background with a certain uncertainty. And LISA is here in black, and you see here the DCRs curve. And for frequency below 40 millihertz, this background is above the binary black hole background that is an extrapolation of coming from the results of LVK. So the problem here is, can we actually resolve, can we in part subtract this extragalactic white dwarf background, or can we discriminate it because of the shape, because of the anisotropy that it can have with respect to the cosmological backgrounds? This is part of the study that we have to do. And in fact, let me transit now to the cosmology of the early universe subgroup. This is quite important because one of the main targets of this new mission of the team I was introducing at the beginning is actually to look at the early universe. And so it will be important to understand how this mission, what else we can learn about the early universe, what are the prospects of subtracting the astrophysical foregrounds, which is quite important, as I was mentioning before. They want to compare advantages and disadvantages of different bandwidths, whether it's the microhertz, the millihertz, the DChertz. It will be important also to put it in context with the plan and possible mission that are also targeting the early universe, including the possible deformation, distortion in the cosmic microwave background radiation that could be also one of the competitors of this large mission in 2050. So I want just to show you here a plot that shows how well this detector can look at the stochastic background with respect to improvement with respect to LISA in the DCRs, Amigo, and LISA Max. I have to say that this is actually a little bit too optimistic to go up to this value because it's not taking into account also the foregrounds that are present at that frequencies. But this will be, I'm sure, upgraded soon. So the last theme I wanted to touch on is, of course, this is the last one, but it's always there, and it's always amazing that we can continue to test general relativity with this detector, of course, much better than what LISA will be able to do. This is just because the signal-to-noise ratio will be larger. We will have a factor 100, 1,000 more events than what we can do with LISA, so we can do statistical tests of general relativity. We can probe the strong equivalence principle with multi-band sources, do spectroscopy with amazing sensitivity, and also map the multiple moments of the black holes for MRI and IMRI, of course, much better, a factor 100, 1,000 better than what LISA can do. So this group is looking into this, and at the moment has been improving the tools to understand how we can probe the nature of gravity during the in-spiral, the merger, and the ring down. So I think I stop here. Oh, I have a minute, so maybe let me go back. I went a bit fast. So I wanted just to maybe then show this plot a moment. So this is quite nice to show how well, depending on the population of massive black hole that we can have, we can obtain the harmonic. So this actually shows the number of events which will have a signal-to-noise ratio larger than 100. Okay, look at this number here, which is quite amazing for the 2-2 mode. And this is the line for the 3-3 mode using Amigo, and this is actually for the DCRs. Okay, I just finished here. I just want to say that there is a great opportunity in 2050 to extend the gravitational wave spectrum from space. So we are trying to prepare the report. There is a lot of work to do. And thank you very much for your attention.
Thanks very much, Alessandra. Very exciting thing to look forward to. Are there any questions? One at the front here.
Hi, thank you very much for this nice talk. I was just wondering, did you ever consider at the decahertz to have kind of 2 LISAs? Because I remember that was the initial concept, and then that will help to break this problem with the cosmological backgrounds, or it's considered to be extremely expensive and non-realistic?
Yeah, so thank you for the question. So until now, we have not been discussing, so in terms of looking at science cases. But to be honest, preparing this presentation, looking back at the white paper, some of the white paper and the discussion in the senior committee, I think, it's maybe unrealistic. But I think maybe the report should say something about that, at least to explain how the science could be, enhanced by having 2 detectors. And who knows, maybe NASA and ESA may have 2 different, missions at the time, or there might be a mission in China. So I believe in the report it will be nice, actually, to have maybe a section dedicated to that. But until now, we have not been discussing that.
We still have time for another question over here.
Hi, mostly a rhetorical question about for the group that's working on the foreground estimation. Are you assuming that you're starting from scratch with this new gravitational wave detector, or are you factoring in that we will have had 4 to 10 years of LISA observations, which has already told us an awful lot about that foreground? And so you're really building off of those observations to subtract even more of the galactic sources. Something I'd like to know.
Yeah, so I just wanted to add that indeed this is something that we want to take into consideration, although we have to also project, because we have, all this work is happening before the LISA mission will fly. So I think we are going to assume that LISA will reach a certain level, and certainly knowing that, we will be able to make our, conclusions more robust. The same is true also for the ground-based detectors. We want to take advantage of the fact that LIGO will be able maybe to have, observe many more binary black holes, binary neutron stars. So even the stochastic background from binary black hole and BNS will be known better at the time in 2050. If not, even Cosmic Explorer and Einstein Telescope. But that will be all a guess, right? Guesswork. But I think we do that.
Okay, I think that's perfect timing. We're down to 0 seconds left.
Ah,
so
wow.
let's thank Alessandra again.